Okay, in this video we're going to give some definitions of momentum and impulse and some quick examples of them. So momentum, linear momentum, is defined, it's symbolized by a lowercase p, and it's a vector quantity, and it is defined as mass times linear velocity. So because it is a vector quantity, we have to always be very careful to define a coordinate system. And so here we will define a traditional coordinate system with positive direction being to the right and upwards. We have mass is a scalar quantity, but velocity is a vector quantity and momentum is a vector quantity. And so we see that the direction of the momentum is the same as the direction of the velocity. The units of this are going to be the units of mass, which are kilograms, times the units of velocity, which are meters per second. And so we have the units of momentum are kilogram meters per second. No special other name for them other than just kilogram meters per second. So just a quick example here. We have, let's say that we have a 5 kilogram mass moving at, let's say here, 3 meters per second. Then its momentum would be equal to its mass times its velocity, so 5 kilograms times 3 meters per second is equal to 15 kilogram meters per second, with the positive here indicating that it is moving in a positive direction, which we have defined to be to the right. If we had the same 5 kilogram mass moving to the left at 3 meters per second, then the momentum here would be equal to negative 15 kilogram meters per second, because we had a negative velocity indicating that it is moving to the left, and so its momentum is also to the left. Impulse is defined as a change in momentum. So we have here impulse, which is symbolized by a uppercase J, is also a vector quantity, is a change in momentum. So the direction of the impulse is the same as the direction of the change in momentum. So a change in momentum, however, if we don't have a change in mass, which in most cases we won't have a change in mass, there might be some instances in which we have a cart moving along and mass being thrown into it, but we'll cover that when we talk about conservation of momentum. We would have, this is a change in mass times velocity, since momentum is mass times velocity. But if the mass doesn't change, this is the same as a mass times a change in velocity, which is a mass times the final velocity minus an initial velocity. So all of these things are true. But momentum itself is not quite a force, or a change in momentum is not quite a force. If we write it out here, a change in momentum is equal to a mass times a change in velocity. It's very close, but it's not quite a force. If we were, however, to consider the rate at which momentum changes, so we have a truck driving down the road coming to a stop, it takes some force to stop it, right? And to find out what force depends on how quickly it's coming to a stop, right? If we just let it coast to a stop, not much force. If it slams into a wall, a lot more force. So if we consider the rate at which momentum changes, then this would be a mass times change in velocity over time. But we have here a change in velocity with respect to time is an acceleration. So this is a mass times an acceleration. So a change in momentum with respect to time is a mass times an acceleration, which is equal to a force. And so we can say here, with a little bit of algebra that the change in momentum is equal to a force applied over a time interval. And we can see that the direction of our change in momentum is the same as the direction of our force, which is the same as the direction of our acceleration. So we have a change in momentum is a force applied over a time interval. This is actually Newton's second law. All it is rewritten in terms of momentum as opposed to acceleration. So Newton's second law. So if we take this, Newton's second law, and we combine it in with what we had up here for all this definition of impulse, we get what's known as the impulse momentum theorem, or the impulse momentum relationship. So an impulse is a change in momentum, which is a mass times final velocity minus initial velocity, which is equal to a force applied over a time interval. So all of these things are true. So we have 4 different things here that we can set equal to each other depending on the situation of our problem. For example, let's say we're given an impulse or a change in momentum and a force, then we can find the time. Or if we're given a change in momentum and a mass and a final velocity, we could find the initial velocity. Okay? So because this all comes back to Newton's second law, we really could use Newton's laws in kinematics to solve these problems, but we can do it in a much simpler way with impulse and momentum. And as you'll see when we talk about conservation of momentum, there are cases in which we have to use momentum and we cannot use Newton's laws in kinematics. But let's have a quick example here. Let's say that we have a mass. We'll stick with our 5 kilograms here. So 5 kilograms moving along. Let's say this was moving a little bit faster, 6 meters per second. And it's on a rough surface. And so we would know that we have a frictional force acting on it, right? We also have, clearly we have a weight acting down, we have a normal force acting up, and we have a frictional force acting back this way, kinetic friction force. And now the change in momentum will be off to the left, correct? So our change in momentum will be back this way, which is the same as the direction of our force, which is causing this change in momentum. Okay, just to clarify that we have the direction of our change in momentum is the same as the direction of the force. But what is this force? Let's say that we notice that after a certain amount of time passes, let's say we have 3 seconds pass, and it finally comes to rest. So the final velocity is equal to 0 after a time of 3 seconds. Well, what was the frictional force acting on this block as it came to rest? So we want to find the frictional force. So we could go through Newton's laws and kinematics here. Maybe we'll do it first that way. So we know that the frictional force will be the mass times the acceleration, right? So the acceleration will be the frictional force divided by the mass. Actually, let me take that back here. Oops. We can find, we first want to find our acceleration. Actually, given that we have a time, we'll use kinematics first. I think it'll make more sense. So we have a time of 3 seconds, a change in velocity. So v is equal to v naught plus at. So the final velocity is 0 is equal to 6 plus our acceleration times the time of 3 seconds. And we would see here our acceleration is equal to -2 negative 2 meters per second. So then the force going through here is mass times acceleration. So the force must then be the 5 kilograms times the negative 2 meters per second. And this is equal to negative 10 newtons. Meters per second squared. Sorry about that. So the frictional force is negative 10 newtons, or the magnitude of that force is 10 newtons. So this is how we could have done it with kinematics and Newton's laws, or we can use the impulse momentum theorem. So let's do it a little bit differently here. So we want to find Fk, the kinetic friction force, and I know that my change in momentum is equal to a force applied over a time interval. So the change in momentum must be my final momentum minus my initial momentum, which is equal to my force applied over my time interval. So the final momentum is 0 since it comes to rest. So 0 minus my initial momentum is just mass times velocity. So we have here minus 5 times 6 is equal to the force applied over a time interval of 3 seconds. So we see, solving for force, we have negative 5 times 6 divided by 3 is equal to our force. And so negative 10 newtons is equal to the force. Or the magnitude of this force, magnitude of this frictional force is equal to 10 newtons. So it's a little bit more straightforward, just because we have only really this one equation to solve for by using the impulse momentum theorem. Although it can be done both ways, this is an example. So simply the force, the frictional force applied over time, is equal to the change in momentum of this. We can see this 6 times 5. The momentum was 30. The momentum here is 0. So force times 3 is equal to 30. The force is 10 newtons to the left.